Hey everyone, Isaac here. In this video, we're going to talk about how you can teleport qubits with entanglement. One can argue that the concept of entanglement boils down to one thing. Does the information of a system of particles equal the sum of its parts? In other words, if I separate out or measure some of my particles, what happens to the other ones? Let's look at a simple example of a 2-qubit state where the 2 qubits are labeled by A and B. We want to ask the question, what happens if I just look at or measure A or B individually? Now I can rephrase this question mathematically by asking, can I write my 2-qubit state as a separable state? If the answer to that question is yes, then I can measure or poke and prod at, say, A without having any effect on B. It's analogous to, say, like how I brewed my coffee this morning and how that would impact the weather in Paris. It wouldn't impact it. So, okay, separable states are a little boring for this reason. So what happens if the answer to the separability question is no? Would that imply that I wouldn't be able to measure or poke and prod at, say, A without there being some effect on B? Let's look at an example where we can't write our 2-qubit state as a separable state. A classic example of a non-separable state is a Bell state. This particular Bell state is an equal superposition of both qubits being in the 0 state and both qubits being in the 1 state. So let's ask, what would measuring A do to B? There are a few interpretations to answer this question, the first one being the wavefunction collapse interpretation. If I measure A, it could be 0 or 1, up or down, say, but let's say the outcome is 0, then the state of A, quote unquote, collapses to 0. But wait, if A collapses to 0, then that means the only possible state that B could therefore be in is also 0. So it's like the outcome of measuring B after measuring A is predetermined. If this process was procedural in that measuring A instantly determines the state of B, then we'd be violating the theory of relativity. Imagine A and B are like on separate ends of the universe. When we measure A, the information that's transferred to B would happen quicker than the speed of light. This is the spooky action at a distance that you've probably heard of. Now, at the time these things were being formulated, this was a thought-provoking paradox, and it has a name. It's called the Einstein-Podolsky-Rosen paradox, EPR paradox. We put some links in the description if you want to learn more about it. But Einstein, Podolsky, and Rosen basically theorized that in order to explain what was happening, there needed to be some quote-unquote hidden variables in quantum states. These hidden variables would therefore kind of explain the reason for this seemingly relativity-breaking phenomenon. Now, long story short, John Stuart Bell, whom the Bell states are named after, put some mathematical meat behind this hidden variable theory, and he was able to disprove the existence of local hidden variables in quantum mechanics. Bell's work didn't disprove the presence of non-local hidden variables in quantum mechanics. There's some nuance to this argument. It's kind of advanced and it's controversial, of course, due to the superluminal part. But we put some links in the description. Have at it if you're interested. So what's the consensus here? What's widely accepted? Basically, you can think of the act of preparing the quantum state as the mechanism for which these seemingly predetermined outcomes happen. But the measurements aren't actually predetermined. We just know that whatever qubit is measured, A or B, and whatever that measurement outcome is, the measurement outcomes of both qubits will be correlated. This quantum correlation that underpins the definition of entanglement is what is endowed to the qubits in the state preparation process. Again, this doesn't mean that outcomes are predetermined or that there are hidden variables. It just means that the outcomes of measurements are correlated. Sort of like how ice cream sales are correlated to hot weather, but just because there's hot weather doesn't mean that I'm going or I'm destined or I must get ice cream, even though I probably will, and it'll be chocolate chip cookie dough. So to summarize, if we have two particles that are entangled, like in the Bell state we just looked at, it's not possible to do things or measure one particle without there being effects on the other one. The widely accepted explanation is that this is just due to quantum correlations that are embedded in the quantum state in the state preparation process. So if you're still a little spooked, that's totally fine. Quantum mechanics, although it's elegantly described by experimentally proven theories, is still kind of mind-bending. Let us know how you interpret entanglement in the comments down below. Do you agree with the widely accepted interpretation that there's just quantum correlations? So quantum mechanics is kind of mind-bending, but it allows us to do some really cool things. So what we're going to show you here is how you can transfer the information from one qubit to another through entanglement. It's important to note that here, teleportation means the transfer of information. It's not physical teleportation like you'd see in Star Trek. But why do we even need to teleport to begin with here? If I want to transfer information from one qubit to another, classically, what we would do is just copy and paste the files that we want to share with somebody. There's not some be-all, end-all USB stick with all of the information on it and it can't be replicated. You just copy paste it. But quantum mechanics doesn't allow us to do this due to the no cloning theorem, which states that there's no operation that exists that can simply take one quantum state and copy it onto another one. Thus, we can only hope of transferring the information, not copy pasting it. The setup for teleportation involves 3 qubits, 2 of which belong to Alice. We'll call them A1 and A2, the other to Bob. And let's say Alice wants to teleport her first qubit, A1, to Bob. So Alice prepares some arbitrary state for her first qubit, A1, but the second qubit of Alice's and Bob's qubit will both start in the 0 state. The first thing we'll want to do is entangle Alice's second qubit with Bob's qubit by preparing a Bell state. This can be achieved by just applying a controlled NOT gate and a Hadamard gate. Next, Alice performs the same operations on both of her qubits, A1 and A2, but in the opposite order. Now pause here if you want to figure out what the full 3-qubit state is after these first 4 operations, but we're going to give it to you right now. The state we get is an equal superposition of 4 different quantum states, each of which has Bob's qubit being in a state that's pretty close to the original state of Alice's first qubit. Now what Alice can do next is measure her 2 qubits and communicate that information to Bob. Based on the information he gets, he just needs to apply a couple of small operations on his qubit, and his qubit will then be in the state that Alice's first qubit was originally in. So to zoom out here, the process is 4 quantum operations, a measurement that then gets classically communicated to Bob, and then maybe a couple more quantum operations applied to Bob's qubit to get the desired state. So quantum operations, classical communication, couple more operations. We can actually move the measurements to the very end of this entire process by just being a bit clever about looking at what operations Bob needs to apply conditioned on the measurement outcomes he receives from Alice. These 2 operations end up being a controlled NOT gate and a controlled Z gate, and that's it. After those 2 operations are applied, the full qubit state has Bob's qubit in the desired state, no matter what Alice measures. It's just a little bit more simple this way instead of measuring, communicating, and blah, blah, blah. So our protocol has basically taken the state of Alice's first qubit and transferred it into the state of Bob's qubit, which was originally in the 0 state. It's kind of miraculous, but you can kind of see how the teleportation is working via a transfer of information. Each operation in our protocol is like a pathway for the information to go through in order to get from Alice's first qubit to Bob's. So if you find yourself with a 3-qubit quantum computer and you can apply some gates to it, you can do some teleportation, or you can just use this simple code and simulate it. Either way, teleportation's pretty cool and it's possible through entanglement. That's all for today's video. Thank you so much for tuning in. If you haven't subscribed already, please do so. Give us a thumbs up, it really helps us out. Leave a comment down below if you disagree with me on anything or you find something controversial. Let's have some fruitful discussions. There's some interesting links in the description. Go check those out if you want to learn more about the EPR paradox, some history behind it, and some interesting discussions on the interpretation of non-local hidden variables. Thanks again for watching, and we'll see you in the next one. Ciao. Okay, we're ready to rock here. In this video, we're going to talk about how you can teleport qubits with entanglement. I could go back to B and teleport qubits. Ice cream sales. Ciao. One can argue. Ciao.